intimidating, but don't worry, we're not going to derive them. I'm only going to show you what they mean and what they imply in practical terms. And we're going to visualize them with graphics that I hope you'll find useful. Objects have something called a charge. This is a property of matter, like mass is a property of matter. In practical terms, what this means for large objects with negative charge is that it has more electrons than protons. The first thing I want you to visualize is that if you have a static object with a charge, it will affect only other charges. And if you have a static magnet, it will affect only other magnets. It will not affect charges. But if you have a moving charge, it will affect a magnet. And if you have a moving magnet, it will affect a charge. At the simplest level of description, that's what these four equations are telling us. It is best to think of this as a field, similar to the quantum fields of quantum field theory that I spoke about in another video. But for visualization, you can think of this as being similar to the gravitational field. The first equation is a formula that tells us how electrical charges create electrical fields. It's based on concepts developed by Carl Friedrich Gauss. It basically tells us that if you have an electrical charge, there will be an electrical field emanating from it. If you want to know the strength of this electrical field, you can calculate it using this equation. Note that the strength of this electrical field is proportional to a constant called epsilon naught. This is known as the vacuum permittivity. This is a property of the vacuum of space. It can be thought of as the resistance of free space against the formation of an electrical field. The second equation is referred to as Gauss's law for magnetism. It's the equivalent of the same equation for magnetism, but it's kind of a negative law. It basically says that if you have the same sphere, but instead of having a charge inside, it was a magnet, you'll never find a configuration where the magnetic lines of force always point outward or always point inward. There's always as much field pointed out as there is pointed in. It will be in loops. In other words, a magnet will always have two poles. There are no magnetic monopoles. You cannot have a positive magnet or north pole by itself or a south pole by itself. You might say, well, I can take this magnet and cut out the north pole. Wouldn't that create a monopole? No, you would just create a smaller magnet with two poles. You can keep cutting this in half over and over, and you would always have two poles. The third equation is called Faraday's law. This law basically says that if you move a magnet, you will create an electrical field. In other words, if you change the magnetic field with time, it creates an electrical field. What does it mean to create an electrical field? It just means that you put a charge there, it will be affected, it will be accelerated. This equation tells engineers how to generate electricity from a generator. You can take large magnets and rotate them, and if you put a wire near it, as you move the magnet, then electricity will be created in the wire. This is because there are electrical charges in the metal wire, and as electric field lines are created, these charges will move, creating a current of electricity. The fourth equation is Ampere's law. It basically says that if you have a moving charge through a wire or an electrical current, you generate a magnetic field. In other words, two wires can be attracted to each other if they have current flowing through it. The equation will tell you how strong the magnetic field would be. So if you have a given current flowing through a wire, let's say 1 amp, and you are 1 meter away, how strong would the magnetic field be at that point? This requires another constant of nature called mu naught. This is known as the permeability of free space. This can be thought of as the ability of free space to allow magnetic lines of force to go through it. Note that there are two terms in this equation. One term tells you that moving electrical charges can create magnetic fields, and the second term tells you that moving electrical fields can also create magnetic fields. This idea of magnetic fields being created from electrical fields was Maxwell's addition to Ampere's law.